Asking Grok 3, human input. In general, solids are the densest, followed by liquids, then gases, and finally plasmas, which have the lowest density. They used to call these the four elements, giving examples of earth equals solids, water equals liquids, air equals gases, and fire equals plasmas. Density can be seen within everything that exists. We should include measuring density when we explain anything that exists. Speculate a measuring system of density for the periodic table, then begin to include all other forms of existence to include plasmas like fire, electricity, magnetic fields, and gravity. Grok 3 thoughts. So I'm trying to think about density in a broader sense, not just for solids, liquids, and gases, but for all forms of matter and energy. The user mentioned the classical elements, earth, water, air, and fire, corresponding to solids, liquids, gases, and plasmas. That's an interesting way to categorize things. Now, they want a measuring system for density that includes everything, even things like fire, electricity, magnetic fields, and gravity. First, let's recall what density typically means. For matter, density is mass per unit volume. That works well for solids, liquids, and gases. But for plasmas, which are ionized gases, the concept is similar, though plasmas can have varying densities depending on their ionization state and temperature. But when we get to things like electricity, magnetic fields, and gravity, density might not be the right term, or at least, it needs to be redefined. These are fields or forces, not matter in the traditional sense. For example, in electromagnetism, we talk about energy density or flux density. The energy density of an electric field is proportional to the square of the electric field strength, and similarly for magnetic fields. So, perhaps for fields, density could refer to energy density or some measure of intensity. Gravity is a bit trickier. In general relativity, gravity is described by the curvature of spacetime, which is related to the stress-energy tensor. So, maybe the density of gravity could be related to the strength of the gravitational field or the curvature of spacetime. Wait, but the user specifically mentioned gravity as a form of existence, which might be a bit vague. Gravity is a force or a field, not a substance with density in the usual sense. Maybe they mean the density of the matter that causes gravitational fields, but that would just be the mass density again. Let me try to think differently. Perhaps in a more unified framework, like in physics where everything is described in terms of fields or quantum fields, we could define a density like quantity for each type of field. For instance, in quantum field theory, particles are excitations of underlying fields, and we can talk about the energy density of these fields. So, maybe density could be generalized to energy density for all forms of existence. But that might be too abstract. Let's see if there's a simpler way. Another idea, in plasma physics, there's a concept called plasma density, which is the number of charged particles per unit volume. For fire, which is a plasma, we could use something similar. For electricity, if we think of it as a flow of charged particles, like in a current, we could talk about current density, which is current per unit area. For magnetic fields, there's magnetic flux density, which is measured in teslas. For gravity, perhaps we could use gravitational field strength, which has units of acceleration, or maybe gravitational potential energy density. But this seems a bit piecemeal. Is there a unified way to define density for all these things? Wait a minute, maybe we can think in terms of how much stuff there is per unit volume, where stuff could be mass, energy, charge, etc., depending on the context. For matter, it's mass density. For energy fields, it's energy density. For electric fields, it could be charge density or electric field energy density. For magnetic fields, magnetic field energy density. For gravity, perhaps the density of the stress-energy tensor, but that's getting into general relativity. Alternatively, perhaps we can use the concept of intensity or concentration. But let's try to be more concrete. Maybe we can categorize different types of densities. Mass density, for solids, liquids, gases, plasmas. Energy density, for fields like electric, magnetic, gravitational. Charge density, for electric fields. Current density, for electric currents. Flux density, for magnetic fields. But this still feels like a list rather than a unified system. Perhaps the user is looking for a more philosophical or metaphorical measuring system, not necessarily a strict physical one. In the context of the classical elements, earth, solids, has high density, water, liquids, medium, air, gases, low, and fire, plasmas even lower. But actually, plasmas can have a wide range of densities, from very low in some astrophysical contexts to relatively high in laboratory plasmas. Moreover, fire isn't exactly a plasma, it's more of a chemical reaction involving hot gases and sometimes ionized particles, but not necessarily a fully ionized plasma. Anyway, perhaps we can think of a scale where solids have the highest mass density, liquids have lower mass density, gases have even lower mass density. Plasmas have variable mass density but often lower than gases. Then, for fields, we could think of their intensity, or strength, as a kind of density. For example, a strong electric field could be said to have a high electric density, but that's not standard terminology. Alternatively, maybe we can use the concept of how much effect or influence something has per unit volume. But this is getting vague. Let me try to think about the periodic table first, as the user mentioned. The periodic table lists elements, which are typically in solid, liquid, or gas form at standard conditions. So, for each element, we can list its density in its standard state. For example, hydrogen is a gas with low density, while osmium is a solid with high density. But that's straightforward. Now, to include plasmas, we could consider the density of plasma states of these elements, but that would depend on temperature and pressure. For instance, hydrogen plasma in the sun has a certain density, but it's not a fixed property of hydrogen. So, perhaps for plasmas, we need to specify conditions. But maybe the user wants a way to compare densities across different states of matter and fields. Another thought, in astrophysics, there's the concept of density in different contexts, like the density of stars, which can be in various states including plasma. Wait, perhaps we can use a logarithmic scale or something to encompass a wide range of densities. For example, the density of interstellar gas is extremely low, while the density of a neutron star is incredibly high. So, a measuring system could be a scale that goes from, say, 10 to the power of minus 30 gram per cc to 10 to the power of 15 gram per cc or something like that. But that still doesn't include fields. Alternatively, maybe we can define a generalized density that incorporates both mass and energy, using E equals mc squared to convert energy to mass equivalent. So, for fields, the energy density could be converted to an equivalent mass density. For example, the energy density of the cosmic microwave background radiation is about 0.25 electron volts per cc, which can be converted to a mass density using m equals E c squared. But that would give a very small mass density, much less than that of interstellar gas. Similarly, for the Earth's magnetic field, the energy density is b squared, 2 mu, which is also very small. So, in this sense, we could compare the density of different things by their equivalent mass density, including both matter and fields. That might be a way to unify the concept. For gravity, the stress-energy tensor includes both mass energy and momentum, so its density could be related to the curvature it produces. But perhaps for simplicity, we can stick with energy density converted to mass density. So, to summarize, a possible measuring system could be: for matter, solids, liquids, gases, plasmas, mass density, ρ equals mv. For fields, electric, magnetic, gravitational, etc., equivalent mass density from energy density, ρ_eq equals ev c squared. Then, we could compare, say, the density of a solid to the equivalent density of a strong magnetic field. For example, the density of iron is about 7.8 grams per cc. The energy density of a 1 Tesla magnetic field is b squared 2 mu, approximately equals 4 times 10 to the power of 5 J per cubic meter. Converting to mass density, ρ_eq equals 4 times 10 to the power of 5 J per cubic meter, c squared approximately equals 4.4 times 10 to the minus 12 grams per cc, which is minuscule compared to iron. So, in this system, matter generally has much higher density than fields, unless the fields are extremely strong, like in the vicinity of black holes or something. But perhaps this is what the user is looking for, a way to quantify and compare the density of different forms of existence. Alternatively, maybe they want a more qualitative or categorical system, like classifying things based on their density ranges. For instance, high density, solids, some liquids. Medium density, liquids, dense gases. Low density, gases, plasmas. Very low density, fields. Wait, another idea. In particle physics, there's the concept of number density, which is the number of particles per unit volume. For gases, it's related to pressure and temperature via the ideal gas law. For solids and liquids, it's related to atomic density. For fields, in quantum field theory, there are particle number densities for virtual particles, but that's probably too advanced. Alternatively, perhaps for fields, we can think of the density of field lines or something, but that's not quantitative. I think the equivalent mass density from energy density is a reasonable approach. So, to speculate on a measuring system, define the generalized density ρ_gen as, for matter, ρ_gen equals mass density ρ for fields, ρ_gen equals energy density, c squared then. We can measure and compare ρ_gen for any form of existence. For example, water, ρ_gen approximately equals 1 gram per cc air at STP, ρ_gen approximately equals 0.0012 grams per cc solar core plasma, ρ_gen approximately equals 150 grams per cc Earth's magnetic field, ρ_gen approximately equals 10 to the power of minus 20 gram per cc, very rough estimate, gravitational field. For the gravitational field of Earth, the energy density is related to the gravitational potential, but it's complicated. Perhaps we can use the energy density of the gravitational field, which in general relativity is not straightforward, but there are ways to define it. Alternatively, maybe for gravity, we can use the density of the matter that sources the gravitational field, but that would just be the mass density again. Wait, perhaps for forces or fields, the density could be related to the strength of the field, but not necessarily in terms of mass or energy. For instance, for gravity, we could use the gravitational acceleration g, which has units of meter per square second, but that's not a density. Or the curvature, but that's even more abstract. I think sticking with energy density is the best bet. Grok 3 output. To address your query, I'll develop a measuring system for density that starts with the periodic table, covering solids, liquids, and gases, and then extends to all forms of existence, including plasmas, like fire, electricity, magnetic fields, and gravity. The goal is to create a unified way to quantify density across these diverse categories, inspired by the classical elements: earth equals solids, water equals liquids, air equals gases, fire equals plasmas, and the idea that density is a fundamental property of everything that exists. Step 1. Density in the periodic table. Let's begin with the periodic table, which lists elements that exist as solids, liquids, or gases under standard conditions, typically 0 degrees Celsius and 1 atmosphere, though some use 25 degrees Celsius. Density for these states is traditionally defined as mass per unit volume, ρ equals mv, measured in units like gram per cc. Solids. Most elements in the periodic table are solids at room temperature, e.g., iron, gold, osmium. For example, iron, ρ approximately equals 7.8 grams per cc. Osmium, the densest naturally occurring element, ρ approximately equals 22.6 grams per cc. Liquids. Only 2 elements are liquid at standard conditions. Mercury, ρ approximately equals 13.5 grams per cc. Bromine, ρ approximately equals 3.1 grams per cc. Gases. 11 elements are gases at standard conditions, e.g., hydrogen, oxygen, nitrogen, hydrogen. ρ approximately equals 0.00009 grams per cc. Oxygen, ρ approximately equals 0.00143 grams per cc. Generally, solids have the highest densities, followed by liquids, then gases, as you noted. This aligns with the classical elements: earth, solids, is densest, water, liquids, is less dense, and air, gases, is much less dense. For the periodic table, we can list each element's density in its standard state, providing a baseline measurement system for matter. Step 2, including plasmas, e.g., fire. Next, let's consider plasmas, which you associate with fire. Plasmas are ionized gases with free electrons and ions, found in flames, stars, and lightning. Unlike solids, liquids, and gases, plasma density varies widely depending on conditions like temperature and pressure. Fire as plasma. Fire is a complex phenomenon, a chemical reaction producing hot gases, with some ionization making it partially a plasma. Its density is low, similar to or less than that of gases, because it involves heated, expanding matter. For example, the density of a flame might be on the order of 0.001 grams per cc or lower, depending on its composition and temperature. Solar plasma. In the sun's core, hydrogen plasma reaches densities of approximately 150 grams per cc due to extreme pressure, far exceeding typical solids. For plasmas, we can still use mass density, ρ equals mv, but we must specify conditions. In the periodic table context, elements like hydrogen or oxygen in plasma form, e.g., in stars, have densities determined by their environment, not a fixed value. Step 3. Expanding to fields: electricity, magnetic fields, gravity. Now, we move beyond matter to forms of existence like electricity, magnetic fields, and gravity, which aren't matter in the traditional sense. Density as mass per volume doesn't directly apply, so we need a broader definition. A natural candidate is energy density, energy per unit volume, since energy is a fundamental property across matter and fields. And Einstein's E equals mc squared allows us to relate energy to an equivalent mass. Generalized density definition. Let's propose a generalized density, ρ_gen. For matter, solids, liquids, gases, plasmas, ρ_gen equals mass density, ρ equals mv in gram per cc. For fields, electricity, magnetic fields, gravity, ρ_gen equals energy density divided by c squared, ρ_gen equals ev, c squared, where c is the speed of light, c squared approximately equals 9 times 10 to the power of 20 square centimeter per square second, converting energy density, e.g. J per cubic meter, to an equivalent mass density, gram per cc. This system unifies all forms of existence under a single metric, allowing comparison. Examples: electricity, electric fields. Energy density of an electric field, U equals 1/2 epsilon E squared. Epsilon is the permittivity of free space, E is the field strength. For a strong field, E equals 10 to the power of 6 V per meter, U approximately equals 4.4 times 10 cubed J per cubic meter. ρ_gen equals U C squared approximately equals 4.4 times 10 to the power of 8 gram per cc, very small compared to matter. Magnetic fields. Energy density, U equals B squared 2 mu, B is magnetic field strength, mu is the permeability of free space. For Earth's magnetic field, B approximately equals 50 mu T, U approximately equals 10 cubed J per cubic meter. ρ_gen approximately equals 10 squared to the power of 4 gram per cc, extremely low. For a 1T magnet, e.g., MRI machine, U approximately equals 4 times 10 to the power of 5 J per cubic meter, so ρ_gen approximately equals 4.4 times 10 squared gram per cc. Gravity. Gravitational field energy density is complex in general relativity, tied to the stress energy tensor. A simplified estimate uses the gravitational potential energy density. Near Earth's surface, the field strength is G approximately equals 9.8 meters per square second. The energy density is small and context dependent, but for a rough scale, the mass density of the source, e.g., Earth, ρ approximately equals 5.5 grams per cc, dominates gravitational effects. Though field energy itself yields a tiny ρ_gen. Step 4, the unified measuring system. Here's the complete system. Matter, measure ρ_gen as mass density, gram per cc. Examples: iron, 7.8 grams per cc, water, 1 gram per cc, air, 0.0012 grams per cc, solar plasma, 150 grams per cc. Fields, measure ρ_gen as energy density, c squared, gram per cc. Examples: electric field, 10 to the power of 8 gram per cc, magnetic field, 10 squared to the power of 4 to 10 squared gram per cc, gravitational field, context dependent, often negligible compared to source mass. This system allows us to compare iron, 7.8 grams per cc, versus a 1T magnetic field, 4.4 times 10 squared gram per cc. Iron is approximately 10 to the power of 12 times denser. Solar plasma, 150 grams per cc, versus air, 0.0012 grams per cc. Plasma can exceed solids under extreme conditions. Step 5, reflection and adjustments. Your observation, solids greater than liquids greater than gases greater than plasmas, holds for typical conditions, but plasmas like the sun's core show exceptions. For fields, their density is usually minuscule unless in extreme cases, e.g., near black holes. If a more qualitative system is preferred, we could categorize high density, solids, dense plasmas; medium density, liquids; low density, gases, typical plasmas; very low density, fields. However, the quantitative ρ_gen provides a rigorous, unified framework, fulfilling the request to include density in describing all existence. Conclusion. The proposed measuring system defines a generalized density, ρ_gen, as mass density for matter and equivalent mass density from energy density for fields. For the periodic table, it starts with standard state densities, then extends to plasmas and fields, enabling a consistent way to quantify and compare the density of solids, liquids, gases, plasmas, electricity, magnetic fields, and gravity. This approach bridges the classical elements intuition with modern physics, offering a versatile tool for understanding existence.